Well, firstly, I would really like to thank the invitation to be able to participate today in this seminar. I have never heard of creativity, well, at least not by people that were listening to me, at least. I mean, a lot of people don't think I ever have that many people listening to me about things like this. And the other thing is, I'm completely confused about languages. Until now, everything's been in English, and the slides have been in Spanish, and they've been spoken in Spanish, and the slides have been in English. This is great, all these different languages. But what I would really like to reflect on this morning from my experience as a lecturer at university and also as a researcher, and I try to teach and train new researchers. There's a certain concepts that I think are very important to take into account, but basically they are based on my experience and what we do in biomedicine. What I would like to present this morning is what is the relevance of creativity in science? What role does it play? How do we or how can we manage to stimulate this creativity, first of all among students and then also within our research groups? And also, how can we select for creative researchers? How can we finance these researchers, and if there exist any structures that can strengthen the creativity amongst scientists beyond what we can think or understand. Normally, creativity has always been associated to artistic activities, painting, art, literature, but much less to science. However, we have to face challenges like understanding how our brain works, how you can get mutant cells, or how does a genome replicate. Nobody even has seen it, or nobody even knows what it is. So the way I see things is that the discovery of new knowledge, the technological innovation, or the way to solve problems, biological problems, from new perspectives, for me, are very clear examples of creativity in science. In creativity, normally we have questions that we want to solve, and that's the best we try and resolve these issues. We have there are discoveries that go beyond the ones that have always been explained, that changed humanity, for example, but there are also discoveries that are smaller scale, but they're still very important because they allow us to change paradigms, way to understand things as have been conceived in their day. But in those cases, this wasn't always obvious just due to our previous knowledge. For example, an example of this type of science that I'm explaining are the results that were got from these for Dr. Yamanaka, which allowed them to be awarded the Nobel Prize in Physiology this year. Until now, they had known that once cells had been, differentiated, we had one in muscles or in our liver, and there they were, and that's where they remained. But they were able to demonstrate that you get cell from anywhere in our body, add 4 genes to it, and that meant that cells all of a sudden could be differentiated in 4 different types of cells, or in different types of cells. Previously, everyone thought that was impossible, and now it can be done. This means that we have to understand the evolution, the development of our bodies in a completely new manner. We have to rewrite all our textbooks, and this now opens up new opportunities for analysis and therapies just based on a discovery in 2006, and this year the importance has been recognized with the Nobel Prize. The research that really needs a dosage of creativity is what we know as transformative research. It is the sort of research that's really going to change a paradigm. It's going to mark a difference from things that we knew and that we're going to know after these research projects. So this, as we call this frontier research, is that creates unexpected observation based on the knowledge or previous knowledge, and they're now useful to generate new innovations, methodologies, and even open up new fields. But what is the problem with this type of research? Well, it has a very high risk factor that it won't work, it will fail. But also, when it does work, it's that really has the largest impact on the progress of science in itself. This is something that is really being developed very recently. For example, 10 years ago, nobody ever talked about frontier research, transformative research. But now it seems more relative to add a touch of creativity to what had been used in the past. And now it means that the contributions are much more interesting. For example, there are reports from the National Science Foundation or from the European Council that say we need scientists who have an exceptional creativity, who are those who can offer much more innovative approaches, and those who can think outside the traditional paradigms. They have to be outside-the-box thinkers. So we have a challenge to do this. So how can we educate these new scientists so that they will be able to carry out this transformative research and this frontier research in the future, in the near future? So to do this, the first we do is we obviously get students, they come from school, and they come to university. And so what do we find? Well, basically, what we can do with these students depends a lot on their previous education and the stimulation of the creativity that they have had in the past. Obviously, we need to offer basic knowledge because obviously they need that so that that's needed to build anything, really. But that doesn't mean that we can't stimulate this creative thinking, and therefore this means that they can be, our scientists can be really good scientists in the future when they finish their degrees. But we have a problem. The problem that I come up against every day when I have to go into a classroom and there's 150 students. They stimulate creativity in a group of 150 people. It's not necessarily impossible, but obviously it's relatively difficult. One of the problems that we came up against was not only do you have to, deal with that, but you also have to transmit knowledge, and based on that knowledge, we have to build something else. So what we've tried is to solve this problem basically by having we have less big groups and more groups of smaller amounts of people. So we've broken down the size of the groups. So what we do is to try and stimulate creative thinking, all these different ideas, and just so we have subjects that are based on problem solving. Instead of doing it in groups of 120 students, we do this in groups of 15 or 8 students, whatever. That is really where we're able to work a lot more to stimulate this type of situation that really stimulates the students to think more rather than just sitting down and studying a book of the textbook. But here, this would be the typical example that I gave last week at school in the 3rd year class of cellular biology. Well, I'm not going to explain exactly what this means. You don't need to worry about that. But really, the basic issue was that you had to understand what was there. So we got the basis of this, what experiment had been carried out, what was the result, where were the controls, what was the sense behind all these experiments? But at the end of this 15 minutes, we said, right, the conclusion that we came to behind that is that we didn't know one thing. So the next question was, how would you do it? What would you do to know what was missing? Well, 45 minutes debating on this question here, on this question mark. We gave no more details, and we didn't carry out any more experiments. So when we start to argue or debate with the students what they would do to find or resolve this question mark, so this is where you see the big difference that there is between students. Some students immediately they see it. They don't see one option. They see hundreds of options, 90% of which make no sense whatsoever. But I never say that, obviously. The real idea is to say, hey, maybe this in 10 years' time we would be able to do it. Now, not, because technically it's not viable and we're not able to do so. But it's a good idea. And that is when really you can see and you're stimulating these students, because, you know, the fact this is relevant or not is not the important thing. The thing is how we actually approach the situation. That's the important thing. So therefore, stimulating creativity at university is a key factor to educate our future scientists with these open minds. They need to have open minds. I think the next step that we come up against is when now they finish their degree and they come to the labs. They go to work in the labs. So what happens in that situation? Obviously, we're not going to teach creativity, but what we can do in those situations is to ensure or stimulate their creativity. And that is, as group leaders, we have a very important role to play. It's key to actually strengthen this so that in the future these students will become good researchers with maybe a different style than has been practiced to date. But obviously that has certain implications. It's not easy because students don't come along and say with a bad idea and you say, you know, that is a bad idea and just do the experiment. I said, well, that's an easy way out, obviously. But really, if we change the style of leading that group, the style where you have interaction with students, that is where you start to sort of build up this trust, this relationship that will allow you to explain the ideas, because maybe initially they won't have a good idea, but after they've been there with 3 or 4 years, they come up with brilliant ideas and fantastic ideas, some of them. Others never get there. So how do we manage to stimulate that? Well, by stimulating their abilities, by carrying out a lot of interaction in group meetings, in interdisciplinary seminars, and offering intellectual and technical backup so that this can all be developed and we end up, you know, training really good scientists. Once these scientists are trained, how can we then choose the right places or things for them? You know, when we say we want creative scientists, because these are the ones that are going to mark the difference in the future of science. Everyone see that's obvious. Obviously, that's what we want to choose. But the reality is completely different. In fact, the scientific organizations, universities, obviously they fund people who fund us, even the institutes themselves choose people, but not necessarily based on that. Their selections are based on established criteria, established rules and regulations that don't precisely put a high value on people's creativity. Basically, it's if they've been able to produce, if they've got a good CV, and then, of course, the selection is done by peers. So therefore, when people propose something strange, they hear, hey, he's gone mad, he's crazy. Instead of actually sitting down and analyzing what he's proposing, you know, in the true sense of the manner. There are facts and figures that we have related to this, and what you have to do is to choose for researchers, especially young ones. it has been seen that when we analyze the people who've been awarded Nobel Prizes, what led them there, they always did, or the majority of the cases, it was due to work they'd done when they were under 40, the majority under 40 and some under 50. Obviously, there's always exceptions, but in general, that are the figures. So what we're saying, i.e., if we want to choose researchers, maybe we should center a lot more on looking for the right people and not on the actual projects themselves, which are the ones that are going to be funded. I'm going to offer you an example of two institutions that have put in a lot of effort to choose this type of people, and not just people who are just well established. But there's something I would like to talk about now, and this is related to funding research. What happens if you have your own group and you receive or you have to ask for finance so that the group works? We are stimulating from different, are we stimulating creativity for science or not? Well, in general, no. Obviously, science in itself is considered to be creative, but what I wanted to say is that if we change the scheme or the way we finance things, this could go hand in hand with different styles of group leaders that we have in our labs. I'm just going to offer you an example now. There are two financing units in the States. They're very, very important for biomedicine. One is the Howard Hughes Medical Institute, and the other one is the NIH, which is the National Institute of Health. Both of them have enormous amounts of money, and they both finance research projects in biomedicine, but quality projects and quality finance. But they have very strict criteria, and they only finance things that are of a really high quality. But the way they consider them are different. For example, Howard Hughes, which is a private foundation, what they do is they finance researchers. They say, this researcher, I like what he does, I like how he does it. He is the person I'm going, or she is the person I'm going to finance. And they get a 5-year period of finance. And basically, 85% of them will then have another period, so another 5 years. So it means if you go to so it means that if you get 5 years, you normally get 10 years because they renew it. So what does this really allow you to do? Exactly what you want to do. And in fact, this is the slogan they use to stimulate that projects go well beyond the ones that will just get results the next year. They want risks to be taken, that they explore unproven avenues, and they want to embrace the unknown, even if it means there is a chance of failure. But you even get a 10-year funding for that to demonstrate that nothing is wrong, that at 5 years' time you fail. If you change your idea, we can maybe look along other roads and other paths. But in contrast, we have the projects that are financed by the NIH. They're 3-year projects in general. They have different types of projects, but the most common ones are these, which are RO1s. And basically what they do is that each 3 years, you get a new project, and if you've been successful in the previous project, well, then you'll get another 3-year project financed. And this is what happens in our country. This type of projects are the ones that we have to ask for renewal every 3 years to get finance for the work we carry out. Well, when we see this, what do you see? Well, when you analyze the data of the results, this was a study that was presented, and it's very serious. In fact, I had to put a graph. I'm sorry, I'm a scientist. I need to put a graph up here. This is a serious study comparing people of similar quality when they started, financed, the red by Howard Hughes or the blue by the NIH. What was seen that the number of papers that are published, which is what we use as a benchmark to see what a lab's doing in a certain research project, is very similar. This number is similar. Even the Howard Hughes even have a few less. However, when you analyze the articles that have been published in the higher impact journals, i.e. their discoveries that could change things, what we see here is that after 4 or 5 years, you start to be a clear difference between those that are financed by one or other of the institutions. These publish, but they have to survive, to keep getting data, to be able to renew, to continue the next project, but not the ones at the top. They're free, and that's when they start to get things that cause much greater impact. This type of scheme, which seems very reasonable, is now being sort of used more systematically. The ERC, the European Research Council, 5 years ago offered projects along these lines of work. They were projects to look for pioneer ideas that weren't traditional ideas and that were innovative projects, 5-year projects, which could have between 2 or 3 million to finance the group in an important manner so that they could do things that were good. And then the Wellcome Trust, which is the largest foundation that finances research in the UK, but they've also launched these new projects that follow these same lines of action. What they're looking for now are scientists with a high level of creativity. This is all recent. You know, we're talking about 5 years ago. There have been institutes that have precisely dedicated their time to look for this type of researchers. And these initiatives have been very, very important because they have really marked and defined the way to go in the future. The first one that I wanted to mention was a pioneer institute in the 70s. It was founded in Germany, in Heidelberg, and it's known as the European Molecular Biology Lab, the EMBL, and it works on molecular biology. And the idea was to hire young people when they just finished either their post-doctoral era, but they proposed interesting things. They proposed to finance them for 9 years. 9 years they had to leave the institute. And in fact, this institute is financed by all the EU countries. And then these scientists have the possibility of going back to where they come from or go somewhere else and get another job. A similar initiative to that is the Howard Hughes Medical Institution. The Genelia Farm Research Campus is based on neurobiology studies. It also started in 2006. We're talking about things that have happened very recently. And here, basically, what they do is recruit small groups to look at issues related to neurobiology. What do these two institutes have in common? Well, the fact is their style is to promote creativity amongst researchers. They have an exquisite selection process. They also recruit very young scientists. They're very generous with their financing. They don't have to ask for projects every 2 years. They've also got research infrastructures that could deal with anything that is suggested. And there's something else that's very important, and I think it's very interesting, is that they reduce the size of the groups. They ensure that the groups have to think a lot about what they really want to do, not just do thousands of different things. No, they have to look for something and support it and develop it as best they can, which means there's a lot of collaborations with other groups, and this stimulates a lot of translational analysis and multidisciplinary analysis. Well, basically, that's what I wanted to explain about the relevance of creativity when it's applied to science. It's key for us to have creative researchers because they're going to establish a difference in science in the future. Also, it's important, and there's a need to educate these scientists, not from the time when they're going to be researchers, no, but since when they were very young. So they go to schools, to universities, prepared to accept or take on board this challenge. And also we need to adapt all these structures from our institutes right up into our organizational and financing bodies, which will allow them really to carry out these type of scientists. And that's what I wanted to say, so thank you very much.